My name is Jari Järvi, and this talk is about detecting stable surface adsorbates with Bayesian optimization. Many of our modern technologies are based on advanced functional materials. The properties of these materials emerge from their atomic and electronic structure. And to optimize their functionality, we have to know the structure. These materials are commonly blends of organic and inorganic components. Of particular interest is the hybrid interface, in which organic molecules can take various different arrangements. Unfortunately, with our current methods, it can be challenging to detect the structure of even a single molecular adsorbate. With the experiments, identifying the structure from microscopy images can be difficult, especially in a case of bulky three-dimensional molecules. Then, with simulations, identifying the stable structures with a thorough and accurate exploration of the potential energy surface is computationally too expensive. The most stable structure corresponds to the global minimum of the potential energy surface. To identify it reliably, we must explore the full energy surface and also compute it accurately with quantum mechanical methods. For this, we use a new machine learning method called Bayesian optimization structure search. BOS accelerates the structure search by smart sampling of the potential energy surface. In this process, BOS approximates the energy surface by building the most probable surrogate model of the surface. The model is refined iteratively with active learning using Bayesian optimization. Bayesian optimization is a method for global optimization of unknown, so-called black box functions. We start here with the known data of the system, and the data is first fitted using Bayesian regression with the distribution over functions, which is a Gaussian process. Then, with the fitted model, we use acquisition function to determine which point to evaluate next for maximal improvement of the model. In our case, we choose an atomic configuration for the energy calculation. We then calculate the energy with the density functional theory and then repeat the process with the new data point included. And in this way, we then refine the model. We describe our atomic system using chemical building blocks. Here we basically encode our current knowledge of the system into these kind of rigid components. They can be, for example, rigid molecules, some functional groups, or for example a surface slab model. The potential energy surface is then defined in a configurational space with respect to, for example, translations and rotations of the building blocks. Here is an example of a simple one-dimensional model. Here we look at the adsorption energy of a molecule as a function of its height from the surface. In this model, the mean of the posterior function distribution is the most probable model. The variance of the function distribution then describes the uncertainty of the model in different areas. Here we have evaluated 5 energy points, and when we keep on acquiring new points, we see how the model converges and the uncertainty is reduced. Next, I'll show one application of BOS. Here we have studied the adsorption of a camphor molecule on a copper 111 surface. This material has also been studied experimentally with atomic force microscopy, and the images show various different adsorbate structures. Now we apply BOS to identify the stable structures. Our model has 4 atomic layers of copper, 6x4 unit cells, and we calculate the adsorption energy with DFT using the FHI-AIMS software. Our model has 2 building blocks. First, we have the global minimum conformer of camphor, and then we have the copper slab model. we have 6 degrees of freedom, 3 translations of camphor in X, Y, and Z, and 3 rotations, alpha, beta, and gamma. The search area on the surface XY plane is within the orthogonal unit cell. And the adsorption height, which is measured from the center of the molecule to the surface, is in range 4 to 7 angstroms. And we do full 360-degree rotations for all rotation axes. Here is how the search progresses. Here on the left we see all the different energy acquisitions that BOSS is doing. And as we see, BOSS acquires many different orientations and locations of the molecule to converge the complete energy landscape. And on the right we see the currently predicted global minimum. And then from the converged model we locate the minima using the built-in local minima search functionality of BOSS. We identified 8 different stable structures. We have classified them in 2 classes A and B with respect to the location of the oxygen atom in camphor. In class A, oxygen is close to the surface, and in class B, oxygen is higher up or on the side, and one of the hydrocarbons is then closest to the surface. We have confirmed these structures with the full relaxation with DFT, and there we release the building block approximation and allow movement of all atoms. In the adsorption energies of these structures, we see that class A structures have the strongest binding to the surface. And here we also see that the energy decreases in the relaxation by 0.1 electron volts on average. Now we can take a look back in the experiments. In our model, the highest energy barriers for the mobility of camphor are in structures A1 to A4. And also we observed hybridization of the electronic states in class A, which indicates chemisorption of the molecule to the copper surface. Based on this, we conclude that the static adsorbates in the AFM images likely feature chemisorbed camphor molecules. Now we can compare the computational effort of the structure search with BOSS to a conventional method with chemical intuition. We could investigate the stable structures by placing the molecule on each of the high symmetry points of the 111 surface. And in each point we could estimate the best candidates for low energy structures with, for example, 10 different orientations of the molecule, and then relax each of these structures. In this example, we would need double the amount of calculations compared to BOSS, and still we could very easily miss some of the structures that BOSS has identified. In conclusion, with BOSS and DFT, we do global structure search with hybrid materials. We can efficiently build the surrogate model of the potential energy surface and identify the stable structures in its minima. In our study of camphor on copper, we identified 8 stable structures in 2 classes, and with our results we concluded that the AFM experiments likely feature chemisorbed camphor molecules. And we look forward to match the identified structures with AFM experiments in more detail. Here is the link where BOSS is freely available for download. And with this, I thank you for your attention.